polar molecules, and nonpolar molecules. The polarity of a molecule is dependent on the bond polarity, from the type of bonds, and the arrangement of bonds or shape of molecule, which comes down to symmetry. Diatomic molecules are molecules composed of only two atoms, which are of the same, or different chemical elements. And these molecules are dependent on bond polarity only. Polyatomic molecules are molecules composed of three or more atoms. The polarity of these molecules are dependent on bond polarity, and its symmetry. Electronegativity, with symbol En, is an atom's tendency to attract electrons in chemical bonds. Electronegativity increases to the right and up on the periodic table, excluding the noble gases. Here are electronegativity of some of the elements in the periodic table. Notice the trend. It increases to the right, and also increases as you go up. When two non-metal atoms bond, they share electrons. They may or may not share electrons evenly. As an example, let's consider the fluorine molecule, and hydrogen fluoride molecule or HF. The electronegativity of hydrogen is 2.1, while the electronegativity of fluorine is 4.0. Notice that the electronegativity of hydrogen is less than the electronegativity of fluorine. In hydrogen fluoride, the electronegativity is much higher for fluorine than for hydrogen. Fluorine atom pulls harder than hydrogen atom. The electrons are drawn more toward fluorine atom. The electron density is drawn toward fluorine side. So the fluorine atom acquires a partial negative charge, and the hydrogen atom acquires a partial positive charge. The partial positive and partial negative charges creates the dipole, and the direction of the dipole moment is towards fluorine. Due to the dipole, the HF bond is polar. The dipole, or two poles, is a separation of opposite charges that occur due to the unequal sharing of electrons between atoms in a molecule. This occurs on polar molecules or compounds. The dipole moment is a measure of net polarity between atoms in the molecule, or between ions in the compound. We use the arrow to show its direction. For polar molecules, the dipole moment is directed towards the more negative charge. For nonpolar molecules, its value is 0, or no dipole moment. In the fluorine molecule, the electronegativity is same for both atoms. Since they are the same atoms, they pull with equal strength. So the electrons are shared evenly between them. The electron density is spread evenly around molecule, and there is no partial positive or partial negative charge. There is no dipole created, so dipole moment is 0. Thus, the bond is nonpolar. Let's summarize the bond polarity in diatomic molecules. For same atoms, the molecule is nonpolar. For different atoms, it is polar. Let's have a quick test, polar or nonpolar. Chlorine molecule Cl2, same atoms, nonpolar. Carbon monoxide CO, different atoms, polar. Bromine molecule Br2, same atoms, nonpolar. Hydrochloric acid HCl, different atoms, polar. Here are some nonpolar diatomic molecules. F2, Cl2, O2, Br2, H2, and N2. Here some polar diatomic molecules. HF, CO, HCl, HBr, NO, and HI. For polyatomic molecules, the polarity is dependent on two factors: the bond polarity and the arrangement or the shape of the molecules, since we need its symmetry. For the bond polarity, we look at outer atoms, and see if they are the same, or not. For the symmetry, we consider the central atom, and check if it has a lone pair of electrons. If we find that all outer atoms are not the same, or the central atom has lone pair, this creates a non-symmetrical, or asymmetrical molecule. Thus, this is a polar molecule. But if we find that all outer atoms are identical, and the central atom do not have any lone pair, this creates a symmetrical molecule. Thus, this is a nonpolar molecule. Let's consider carbon dioxide, or CO2. This is its Lewis structure. Notice that the outer atoms are identical. And, if you look at the central atom, it does not have any lone pair of electrons. Thus, based on the Vesper theory, its shape is linear. Based on the bond polarity, the dipole moments are towards oxygen. They are symmetrical. Thus, they cancel each other out. In this case, the overall dipole moment is zero. Therefore, CO2, or carbon dioxide molecule, is nonpolar. Now let us consider the water molecule, or H2O. This is the Lewis structure. Notice, it has the same outer atoms, both are hydrogen. However, the central atom has lone pairs. Based on the Vesper theory, its shape is bent, or V-shaped. Based on the bond polarity, the dipole moments are towards oxygen. They are non-symmetrical. Thus, the dipole moments do not cancel each other out. In this case, the overall dipole moment is toward oxygen. Therefore, the water molecule, or H2O, is polar. Let's put carbon dioxide and water side by side, for better comparison. Here is carbon dioxide, and here is water. The carbon dioxide has the same outer atoms, both are oxygen, the central atom has no lone pair. Based on Vesper theory, the shape is linear. Since the overall dipole moment is zero, it's symmetrical. Therefore, the carbon dioxide molecule is nonpolar. Now for water. It has the same outer atoms, both are oxygen, the central atom has lone pairs. So based on VSEPR theory, the shape is bent. The overall dipole moment points towards oxygen. Because of this, it is non-symmetrical. Therefore, the water molecule is polar. Let's have more examples. Here's CH4 or methane. Using Lewis structure, we see that outer atoms are identical, and central atom has no lone pair. There is equal pull of electrons towards the carbon atom. Based on VSEPR theory, the structure is tetrahedral. And the dipole moments are symmetrical, thus methane is nonpolar. Next, CH3Cl or methyl chloride. Using Lewis structure, we see that outer atoms are different, also, central atom has no lone pair. In here, the dipole moments are non-symmetrical. And the overall dipole moment point towards chlorine. Thus, methyl chloride is polar. Let's summarize the two molecules. Methane has same outer atoms, while methyl chloride has different outer atoms. Central atoms have no lone pair, thus, both are tetrahedral. In methane, dipole moment is 0. And it is symmetrical, while, in methyl chloride, dipole moment points toward chlorine. It is non-symmetrical. In this case, the outer atoms were the key factor in polarity. Here is boron trifluoride. Outer atoms are identical, and central atom has no lone pair. The dipole moments are symmetrical. Thus, it is nonpolar. Here is ammonia or NH3. Outer atoms are identical, but central atom has a lone pair. The dipole moments are non-symmetrical. Thus, it is polar. Comparing these two molecules, notice that the main difference is the lone pair in the central atom, which determines their symmetry. In this case, it was the key factor in the polarity. As a guide in determining polarity, you can also use the SNAP method. If symmetrical, it's nonpolar. If asymmetrical, it's polar. Here is a short list of nonpolar molecules. And polar molecules.